yesterday in Carlos's keynote speaker discussion at lunchtime, he talked about the signal program and how it's moving, and it is in a world-class situation, and it's due a lot to these performance metrics that have been developed over the years. So we'll start with some introductions. Mark Taylor is the signal operations engineer for UDOT, who oversees the maintenance and operations of UDOT's 1,250 traffic signals. He has 16 years of experience in the traffic signal industry. Shane Johnson has spent the last 15 years deploying and supporting traffic control systems. He currently works at the TOC developing and supporting signal performance metric systems and the MaxView central system. Jamie Mackey is the statewide signal engineer for UDOT and is responsible for timing at half of the traffic signals in the state. She has worked in the traffic signal operations industry in Texas and Utah. Dr. Saito is a tenured full professor of civil engineering at Brigham Young University and the founding director of the BYU Transportation Lab. He has published numerous technical papers in the field of traffic engineering and traffic operations, and currently is an associate editor of the Journal of Transportation for ITE. Just as we go through, there's going to be two clipboards that we're going to send up both sides. If you're in state, that qualifies you for the continuing education. If you're from out of state and need a continuing education certificate, there's one up at the front that you'll need to fill out and get signed by one of the presenters. So, thanks. Mark.
Good morning, everybody. Really appreciate you all being here. I thought I would begin by mentioning a few brief facts, about us here in Utah. To just give you a brief overview, there's about 1,961 traffic signals in the state of Utah. UDOT owns and operates, about 60% of those. So the other 40% are owned by various cities and the counties throughout the state here. One thing that makes us a bit unique is we share a lot, and the network which we have is shared equally between UDOT and all of the partners. We are probably the only state in the nation that actually does this. And as a result, UDOT has 89 of our traffic, or 89% of our traffic lights hooked up, while the non-UDOT signals, it's about 80%. So we are doing very well there. We are hoping in just a few more years that we are 100%. So we are doing some things right now to rapidly move in that direction. And then, as I mentioned before, the UDOT system we have, the ATMS system, is shared equally between all of the partners. Back in 2011, UDOT's executive leaders gave us an opportunity. They asked us some questions. They asked us, what would it take for UDOT's traffic signals to be world-class, knowing the large return on investment that good traffic signal operations gives? They asked some other questions too. What is the trend? Are things getting better, getting worse, or staying the same, and by how much? And we just didn't have any good answers for these questions that they were asking us. So we did what everybody else would have done, and we formed a quality improvement team back in 2011 to look into the best practices of what we should do to move in the direction of world class. There were some great things that came out of the quality improvement team report. One of those was to require that communications and signal detection be maintained during the construction. Another thing that came out of this was to transition from reactive to proactive traffic signal maintenance. And then last, there were actually 39 things that we actually pointed out, but one of them that we will be talking to you more about today is to implement real-time monitoring of system health and quality of operations. So with that came this project that we have been working on called Automated Traffic Signal Performance Measures, or SPMs for short. So we began in the 2011 moving in this direction. Well, back in just a year ago, in July of 2014, we held a focus group. And if you've ever held a focus group before, they're pretty interesting, but they're humbling. Basically, the way they work is there's a group of men and there's a group of women that sit for the 2 hours in a room. And you are behind a mirror. They don't know you are actually there. There is a moderator there, and the moderator is asking them questions on the traffic signals, what they think of them. And if you could only imagine past experiences sitting in there and hearing them tear you apart. And every time we do these focus groups, I keep on telling my boss, please not again, because it really humbles you. And this time it was a little different. So there were some key findings that came out of the focus group just a year ago, 3 years after we have been asked by our senior leaders to move towards world-class traffic signals. One of those things here was that UDOT is perceived positively with innovation as the primary driver of positive impressions. People like the CFIs, the DDIs, the flashing yellow arrows, the tape that we have on the back plates. They also said, and both the men and the women agreed on this, they believed that traffic signal synchronization was getting better. And they also agreed that UDOT should be more open about the accomplishments. They want us to brag a little bit more about what we are doing and letting the public know that we are changing the traffic signals whenever there's special events going on, and we're out there quite a bit, making things better. People want to know this. So, as a result of the focus group, we made a 60-second commercial that we played in movie theaters for about 3 months last year, and I'll go ahead and run it here.
Green light, red light, green light, red light. Come on! Green light. Green light. Green light. Green light.
Some people were destined to be UDOT traffic engineers.
Green light.
Okay, it looks like we need more green lights on State Street during the morning rush.
They know how much you hate red lights, so they're always striving to get you more greens. Using the latest technology, they work 24/7 to sync the lights, manage incidents and events, and get you where you need to be sooner. Learn how you can help us all get more green lights.
Green light. Green light. Green light.
All right. So I want to just mention a few things here really quick before before we hand it over to Shane, who is one of the software developers for the website that you will actually see here. Benjamin Franklin once said, "Without continual growth and progress, such words as improvement, achievement, and success have no meaning." Parsons Brinkerhoff, they said, "Our success will not be measured by how much data we collect, but instead how we use the data to improve the operation of our transportation network." And then my boss up in Idaho at a conference once said, "Well-measured results that show a high return on investment is the key to receiving additional resources and sustained support." I just want to give a little bit of kudos here to Purdue University and Indiana DOT. A lot of the concepts you will hear discussed here have come from them. They are the ones who have spent over a decade working with the various manufacturers out there to have this high-resolution data logger run. And so our hats are off with the work that they have done. Shane, I'll turn the time over to you.
All right. So before Jamie gets into the website and what we're doing, I'm going to take a few minutes and talk about what it takes to get there and how we got there. So like Mark said, large chunk of this work is due to Purdue University's groundbreaking work on developing the performance metrics, getting the controller manufacturers to the table, and having them see the benefits of implementing the high definition data logging. So a bit about why we need to do this at all. First, to better respond to user complaints, we need to verify whether the problem actually occurred. And not that I doubt what the users are saying, but occasionally they exaggerate. And if we base our efforts off of those exaggerated reports, even if they're correct, let's say even if the user waited for 4 hours at one intersection, that's the atypical experience. So we need to know what the typical driver experience is so that we can better concentrate our efforts. And also, once we have all the data in place, we can much more easily see the solution from our desk. We don't have to drive the corridor. We don't have to put probes out. We can just see the solution, make the changes, see the results, and it's great. So along those lines, we proactively identify and correct operational and maintenance inefficiencies. We can see the problem often before it's ever reported. We don't have to wait for drivers to call. Can improve the quality of progression, improve capacity allocation, and respond quickly to equipment failures. I think that's probably our favorite one. We can see when detectors fail before people call us and get it fixed, and improve safety. All right, so like I was saying, our typical range of operations, that blue line there, that's usually what the system does, but what the users remember is when the system breaks. They don't typically call us and say, I didn't get any green lights on State Street this morning. Yeah, it just doesn't happen. They call us when there's a problem or when they experience a problem, and sometimes that problem isn't necessarily the typical operation of the signal. So gathering this information, displaying it, very useful in identifying what's going wrong and what we really need to fix. Right, so one of the reasons we need a dedicated signal performance maintenance or signal performance metrics system along with high definition data, and because we just couldn't get this information from our central system. Central systems typically pull at once per second. And even if we had a best case scenario where the system could pull 3 times per second, 3 times faster than what we consider real time, which again, almost never happens, we would still miss a lot of information. So these little black dots, let's say they represent detector hits, and we can see the pull response cycle. So when the system pulls the controller, there's a brief orange period up there at the top where the controller formulates and sends its response. Then in the yellow time, it's sending its response back. And then once the response is received, the central system will send out another pull. Well, if the detector hit doesn't happen, essentially in that orange time, the controller doesn't care. It doesn't respond and say, yeah, there's a detector hit there. So we end up missing the vast majority of detector hits. We'll miss other information too, but mostly what we were lacking is detector activations, and that's really where we get into the ability to change timing parameters and make things better, is when we know how the vehicles are flowing through the streets. We could still get some information and some good information from the central system, but it wasn't nearly complete. That's why we needed the controllers to log what was happening at the intersection at about 1/10 of a second resolution. Cars pass those detectors quickly. We need to know just about every single one. All right. So one of the big goals was to get all of the signal controller manufacturers to use the same set of enumerations. We wanted phase 2 turn to green to be recorded the same way in a Econolite controller as it is in a peak controller as it is in an Innolight controller. They all had to be the same, or writing a performance metric system would be different for every single vendor, and that would very quickly become unusable. So several years ago, Purdue University invited controller manufacturers to collaborate and to agree on specifications for the data. From what I understand, 3 vendors initially participated. I sadly wasn't there. But today we've got 6. So most of them are on board, and all of the big ones. So it's been wonderful to see the industry accept this, and I hope it continues. It's been great. So one of the objectives, of course, was vendor neutrality. We wanted everybody's controller to work with the system, and we wanted it to work in mostly the same way. There are still some slight variations, but there are no variations in the way the data is recorded. The only difference is sometimes how we get to the data, and technically that's a small challenge to overcome. If everyone recorded it differently, we would need translator programs and a list of enumerators, and it would just be complete chaos. But since all of the vendors, all of the controller manufacturers are recording the events in the same way, this is actually possible, and it's a great thing to watch. This is a sample of how the events are stored in the controller. So each event has its own enumeration or event code. So say event 0 is phase on, and event 1 is phase green began, on and on and on. The 2 really important ones, detector on and off, those are 81 and 82. There are enumerations in there for pattern changes and what pattern it goes to. Even the program splits per pattern are recorded. There are, maybe a half a dozen that we wish we had that we don't right now, but those are being worked on, and I think we'll see those soon. But all in all, it's very comprehensive. We can see the operation of the controller, and it's recorded 24 hours a day. So it doesn't stop recording at any time. Which is important, and Jamie will get onto why in just a bit. Another view of how the information is recorded. It's time-stamped with up to 1/10 of a second accuracy. So within 1/10 of a second, we know if a detector crossed or a phase change. Then there's the enumeration code in that second column, again describing what happened, and then the parameter in the third column describing who it happened to, or what phase or event. So, and that line, detector 5 is on. We can tell by the event code in the second column, number 82, that means detector on, and then the number 5 in the parameter column, which means the detector channel 5 was turned on. We can see this case, phased green, or phase 8 turned to green, because there's a code of 10, and then, detector off. Oh, you know what? That all slid the wrong way. My slide's bad. But point is, we can parse through these and see what's going on there pretty easily. So a bit about what it takes to make this happen, which is always the interesting part, I think. First, we need high-resolution controllers. We need controllers that are capable of logging these. Most modern controllers will do it. If you're still working in the ASC2 phase, 10 or 15 years ago, you've got to upgrade the controllers. But the ASC3s, the max time controllers, peak controllers, the new TrafficWire ones, they'll all do it. You need good comm to the intersection. Right now, it only works over Ethernet. The reason for that is because we either retrieve the controllers over FTP or through a web server, or we retrieve the logs over FTP or through a web service. And those 2 programs only work over Ethernet. There's no capacity to do this over serial connections currently, and I highly doubt there ever will be. The other option, if you do not have Ethernet to your intersection, is you can record the events locally to a little flash drive, and then run out to the intersection every time you want them, and grab those off the flash drive, and then read them into your system. You need a server that's capable of retrieving the logs and storing and translating the logs and storing the logs into a database. And you're going to need a web server that's capable of interpreting the logs and displaying them. Oftentimes, those two servers can be the same thing, but if your system's really, really big, it's better to separate those functions out to two different pieces of hardware. And of course, you need detection to show what's happening at the intersection. Like I said before, there are some metrics you can use without detection that are important and very useful, but if you have detection in the street, that's when things really take off. And importantly, this can all be done independent of a central system. We do not need, we don't need a central system to store or display these logs. Really useful if you want information to get out to the public or planners or municipal organizations, and you don't want those people to have access to your central system where they can interfere with your timings. We don't have to provide usernames and passwords or VPNs. We can just point them to the website and say, here's all your information. Our consultants use this, a whole bunches of people use this outside of a central system, and it keeps the signal maintenance tasks away from the information mining tasks. Huge gain. Okay, so this is a list of controllers that support the high definition data logger right now. Like I said, we've seen a lot of acceptance from the industry. We've seen a lot of acceptance from the industry for these data loggers, and that's exactly what we wanted. We wanted wide enough acceptance so that it became a de facto standard, even if it wasn't a mandated one. So the more people that supported this, that started using it, that insisted in their RFPs and to the people that they talked to that they had to have this feature, the more it become accepted, and the more the industry would just implement it. And it's been working very well so far. Very happy with it. All right, so at the heart of this entire project is our fiber network, and we are almost unique in the nation with our fiber network. Like Mark said, we talk to 80% of them throughout the entire state. There are small towns that don't get that much coverage from their fiber network, but we get it throughout the entire state. And it has not come without effort. Lynn Yocum's efforts are largely to thank for this. But this slide in particular, I think, is important. We own hundreds of miles worth of fiber, but even that's not enough. So the way we really grew our network was by bartering with other providers, cable providers, internet providers, that sort of thing. So as we cut open the freeways and put down conduit, even if it's empty, it needs to be there so that we can trade that capacity with other providers. So if you look at this graph, the dark blue is what UDOT actually owns. And in 2001, it was the majority of it. Stuff that we put in. But right around 2007, all of a sudden, our bartered fiber, starts to become the majority of it. So that now, most of our fiber, even though it's maybe 56%, is stuff that we've bartered instead of put in ourselves. So that's really the way to get ahead, is to cooperate with these private entities, trade capacity, and all of a sudden we can extend our network to places we never thought possible. All right, a bit about the kinds of controller metrics we can get with the different kinds of detection. Like I said, once we have detection out there, things really take off. If we don't have any, or we just have stop bar detection, we can get things like the phase termination report that shows how each phase ended throughout the day. Hugely important. Jamie will go into the reasons why, but I think that's the one we use most, right? Phase termination. We can get the split monitor that will show the capacity of the splits for each cycle, and we can adjust the timings based off that. And we can get an email of daily issues, either lack of communications or certain detector issues. So if we have advanced detection, which is a detector placed on the approach about 400 feet or more away from the stop bar, we can see things like the Purdue coordination diagram, which shows where the cars arrive in the phase, approach volume, platoon ratios, which cars arrive on red. We can calculate the approach delay, how long we think the average vehicle has to wait at an intersection. We can show interesting executive summary reports that are prepared to give to senior leadership. And we can use the link pivot, which is an innovative little tool that I'll let Jamie talk about, but is pretty cool. Also with advanced detection, if you are using the Wavetronics detector, theirs is the only one that does this right now, we can find out what the average speeds are, or at least actually speed of every single vehicle that crosses that detector. So it's better than average speed, it's actual speed of the vehicle. We can see lane by lane detection if we have a lane by lane detector. And from that, we can see a split failure metric that we're still developing. We can also see lane by lane volumes, turning movement counts, that sort of fun stuff. And the yellow and red activation chart, which we'll get into in a bit too. That's what I thought. Anyway, I had one more. If we have probe travel time data, we can display a report that shows the average travel times throughout our arterial system. And except for the speed metric, which requires the Wavetronics advanced detector, it doesn't really matter which detection technology we use. We can use video, we can use loops, we can use radar, can bury pucks in the ground. Yeah, all of them work, and we've used almost all of them on the system. Okay, so we grab, the way this works on the controller, just to give you a quick rundown, is the controller is obviously running the signal. And at the same time it's running the signal, it's recording every little bit of what it's doing in a compressed binary file. These things are super tiny, about 10 kilobytes per hour of information that it stores in there. Extremely, extremely compressed. And so we retrieve those using FTP usually. There's one controller out there that uses a web service, but we retrieve those over the network. We store them on our controller, and then we store them on our server. Then we decode them, and all of a sudden they grow by an order of 10. So if they're really small on the controller, we explode them, and they become much bigger on the central system, and then we read them into the server. We do that file collection, like I said, over FTP. So if you're setting this up, it's important that the server and the controller have a clear FTP path between each other. It might require some firewall changes. And once we get them on the server, then we've got to do something with them. And this is a screenshot of what our database server looked like about 3 days ago. With the exception of the C drive, which is where the operating system is, and the exception of the D drive, which is temporary storage when we don't use, all the other numbers there are measured in terabytes or 1,000 gigabytes. So way back in 2012, we started out with 8 terabytes, and we ran through that really quick. And so we bought an expansion drive that gave us an additional 10. That bought us about a year and a half. And then we carted in as quickly as we could, really. Carted in another 20 terabyte drive that we've only got like 6 terabytes left on it now, right? So yeah, we've got to get more storage. So at the data storage rate is about 10 megabytes per controller per day. Not a lot if you're only dealing with 1 or 2 controllers. We've got 1,700. It's a lot. It's gigabytes per day. I mean, it's massive. So we grow quickly, and it's one of the constant challenges for anyone looking to implement or maintain this is how to get enough drive storage. The only good suggestion I have there is have a lot of funding in place before you start. But for small systems, it's really not too unmanageable. For statewide systems or large city systems, it's something you certainly have to keep in mind. But we've been fortunate. We've had support of our leadership that sees the value of this project, continues to support the funding, and it's been going on great so far. James.
Hi, everybody. Thanks for having us today. Thanks for coming. I'm going to talk to you about the actual website operation, how it works, how you can use it to do your job a little better as well. This is our website. It's u.traffic.utah.gov/signal performance metrics. And if you can't remember that, I made a comment on our Whova app for this session, so you can go there and read it in your own leisure. The website itself was written primarily by Shane here and one of our other programmers, done completely in-house. Mark and I, provided direction, so it's been a really great way to make sure we're getting exactly what we need, and we've been really happy with it. And Mark will tell you later about how we're trying to help other entities around the states, get this as well. I'm going to talk about how I use the metrics first primarily and how we're using this to make the traffic signal system in Utah better. And then after that, how you can use the website. This is called the phase termination chart. It's pretty simple, but it may look complicated at first. Where's my thing? Down here along the x-axis, we have time of day, so midnight to midnight. So that's 1 day of data showing there. Right along the Y, we have the phase. So if you don't know, every movement at an intersection has a phase. The odds are primarily left turns. The evens are going to be your through movements. The little colors here for each dot, that's not working. Oh, first of all, you can look at this really quickly and see how the signal, what it's doing throughout the whole day. So we generally have a free operation up until 6 a.m., and then we run different plans. You can see that along the top here. We run different plans until about 9 o'clock at night, and then it goes back into free. The little green dots, every time that signal turns green, it puts a dot on the map or on the chart. And this is not liking me. The green indicates that that signal gapped out. So the detector was on while vehicles were there. It still had extra time to give that movement, but the detector indicated no one was there. It gapped out and then moved on to the next phase. If there's a red dot, that happens during free operation when that movement used 100% of its time. And the blue indicates during coordination that it used 100% of its time. The little dots above the signal phase data show pedestrian actuation, so we can easily see how often that pedestrian movement was called. And if you don't see any dots, that means that phase was skipped. So this is a good example of an intersection operating fairly well. You can see in the PM peak here that almost all the movements have quite a few blue dots, so that may indicate that we're either at or over capacity. But generally throughout the day, you see mixes of blue and green, and that's what we like to see. So this is an example of a problem we used to have very frequently. We would get phone calls from someone saying, I left work at 2 a.m., and the signal turned red on me, and then I waited for like 40 seconds or 2 minutes, whatever they want to say. And then finally I got my turn and I drove down the street and I looked behind me and I saw that the signal turned red again for no traffic. And, then they were mad and they maybe said bad things to us. Then I would send my technician out there, and I've got a few of you here in the audience, so you'd appreciate this. I'd send them out there, they'd get there at noon, and the signal's working just fine at noon, so now they're mad at me too. So looking at this, I can quickly diagnose the problem. The problem is occurring for phases 4 and 7 in the middle of the night only. This is likely a video detection problem where maybe we don't have any street lighting and the detection goes into a fail-safe mode. So now I can tell our technicians, I can say the problem occurs between 1 and 6 or 7 in the morning, and that's probably when you need to get out there to troubleshoot it. It's working fine during the day. And so we've fixed that problem much more efficiently this way without a ton of back and forth. And this is how it looks after the problem was fixed. You can see that phase 7 rarely comes up at all in the middle of the night, and phase 4 only comes up occasionally. So you can see why the traveling public was a little upset. Okay, so we took that concept, and it seems like it's pretty simple, A monkey could do it, or at least in our hope, a computer could do it. So this is showing you a day and a half of data for that phase termination chart. You can see here the first evening that everything looks just fine. Lots of green dots. That's really all you should ever see in the middle of the night. Second night, a solid red line. That phase is suddenly maxing out. You can see it happened right here at about 11 a.m. A solid blue line turning into a red line and back to a blue line. So why not catch that as soon as it happens? So we developed a metric that will evaluate the operation between 1 and 5 a.m. in the morning, and if it finds a phase that has over 90% max outs or force offs, it generates an alert that we get at 7 a.m., and so by 9 or 10 a.m., we have a work order out for that. The technicians get to it a few days. We don't receive complaints anymore about it. We get to it before the public really even notices. This is what that email looks like. It simply lists the intersection and which phase it is, and so then it's up to us to go double check that metric, see what troubleshooting we can do remotely, and if it truly is a problem, we write that work order. Another metric we have is called yellow and red actuations. We have a sensor just in front of the stop bar. It's a count sensor, so it only goes, when a car crosses over it, it puts in one count, and it only looks at vehicles traveling more than 20 or 15 miles an hour. We look at those actuations during the yellow and the red intervals to see if we have a problem out there. So you can see this intersection, Foothill Drive, leaving the University of Utah, is generally fine throughout most of the day. We have a few people going through on yellow, which is exactly what the yellow interval is for. This red interval, we should not have anyone crossing the stop bar. The red interval is intended for people to get across the intersection out of the way. And so in this case, we have a 2-second all red is what we call that. And then the next phase starts its green after those 2 seconds. So this sort of pink color at the top indicates that another movement had a green light. So we certainly don't want to see any actuations during that time. In the PM peak at this location, we have pretty excessive delays for vehicles, and they're really desperate to get through to the next signal. And so vehicles are starting to kind of push that red a little bit. And it worries us a little bit to see these vehicles crossing that red line right at the end of that all red period. It creates inefficiencies in the signal, so now the people trying to come across have to wait for that traffic, and then they're more prone to start running that light, and it becomes this big problem. So when we find this metric has helped us to find locations at our signals where we may be having these problems. It won't always be with people intentionally running the light. It could just be, though, in this case, where they're probably mad and they just want more green time. It could be that our coordination is not great and we have a large platoon of vehicles that we're turning red right in the middle of them and they're just not prepared for the signal to turn red. It could mean that they don't see the signal very well. Maybe they're coming around a curve and they're sort of surprised by it. Or it could just be that maybe this is a great location for law enforcement to come out. And that maybe if we evaluate it to be a problem, we might want to inform them. This is my favorite metric. It's called the split monitor. This is the one that I use multiple times every day. It shows the same information as a phase termination chart. So every single time that phase turns green, it shows a little dot on the screen. Green indicates gap out. Red and blue indicate that it used 100% of its time. And you can see the pedestrian actuations as well. In this one, we're again looking midnight to midnight. This time we have one chart per phase, and the y-axis indicates how long that signal was on for. So the red line here indicates the programmed split at that time of day. So that's how much time that phase is programmed to receive. You can see in the AM that this phase actually gets quite a bit more time frequently. So the other phases are gapping out early. This phase can borrow that time. And so it looks like most of the time it's using 100% of that movement, but it's getting much more than the 28 seconds or so that we gave it. Middle of the day, the phases are mostly gapping out. In the PM peak, again, we're using 100% of the time, but in this case, the whole intersection is fairly full and it's not allowed to borrow time from someone else. So what I can do looking at this map quickly, if I receive a complaint from someone saying, I'm not getting enough time, we get that a lot, I don't have enough time, and before we're never sure what that meant. Is the detector broken? Is the phase too short? Can we get time from someone else? And so now I can look at this, and if they say my problem's at noon and I'm not getting enough time, the operation to me looks just fine. But what it might be is that the detector's not working very well. And so I can go and dispatch one of my maintenance technicians to go look and double check that that detector's working well. If I receive that complaint in the PM peak, I know it's not a detector issue because they're getting 100% of their time, and now I can have an engineer or a timing technician go out there and evaluate if any of the other movements are not using all of their time. I can use a split monitor from the other phases to see if anybody is not using their time maybe after this phase, and if I could maybe switch my phases and or reduce some of the splits on the others to give this phase more time. This is called the Purdue Coordination Diagram. This is our first metric that I've shown you that uses the advanced sensors. So again, these are like 400 plus feet behind the stop bar, and the goal is to put the sensor behind any standing cues we might have throughout the day. And what it does is every time a vehicle goes over that sensor, we then calculate when we expect that vehicle to arrive at the stop bar and then match that up with the phase information. So again, midnight to midnight on the bottom, and this time it's time and cycle up the Y. So the signal, this phase was red at the 0. It continues to be red until the green line, which indicates that the signal turned green. It's green in this part, and then this is when it turns red again. So every line up is a new cycle for that phase. The little black dots show that a vehicle arrived at the signal. I forget that these things are here. So the black are people arriving at the signal. You can see that for most of the day, we have this big density up here. And that's what we want to see. This looks like great progression to me. And I do not have example of poor progression, so you should just imagine that. Everything looks like this. If we look a little closer at the midday plan, we have some data at the top here. It shows that I have 84% of my vehicles arriving on green, with only getting about 50% of the green time, which is really spectacular. So we have a platoon ratio of 1.8 or so, which means, so that's the ratio of vehicles arriving on green to the amount of green time they have. Overall, this signal has a 78% arrival on green. That's really, really good. And if we have free operations, so you can even see here on the right, in a free operation, we assume that vehicles are arriving randomly. So our best hope is that we have a platoon ratio of 1. So if I give that movement 50% of the green time, I would expect 50% of the traffic to arrive on the green. And so that's the whole point of coordination, is to get that platoon ratio higher and get more people through with the limited amount of green time we can give them. Approach delay, we can take that chart I just had, and this is not HCM. Anybody who loves HCM might just want to close your ears. This is just purely saying if a vehicle arrives right at the beginning of red and they wait for 30 seconds until it turns green, that they have a delay of 30 seconds. If they arrive 10 seconds before it turns red or before it turns green, then they have 10 seconds of delay. And so it helps us in a general sense to know when we have the most delay at the signal. So you can see PM peak was the worst, and that's the time where we had the most vehicles arriving here at the beginning of red. So we can use this and compare it to other intersections, and then we can scale that up and start more objectively figuring out where we have the worst problems in the state, not just where I drive home and where these guys drive home, or where we have the most vocal phone calls from too. So we can take that Purdue coordination diagram, and when we have that for every approach along a whole corridor, Purdue University came out with this metric called link pivot. And it's extremely powerful, and it's our first real step into optimization through this, not just raw data and displaying it, but actually how do we optimize our system. So we have some predefined corridors up here. You pick a date, time, cycle length, run it, and this is the data that it gives me to look at one link in there. So in this case, I'm showing you an example on Foothill Boulevard between Sunnyside and 21st East. And the link pivot works by looking at the exit approaches on that link. So what this is indicating is that once it ran through its simulation, it feels like a 16-second change would be beneficial, and that would give me about a 12% increase on arrivals in green in one direction and about 6 in the other. So what it does is it takes that Purdue coordination diagram and it offsets the detection 1 second for every second in our cycle length. And at the end of that offset, it just sums up how many vehicles are now arriving on green and develops this little chart. And you can see right here, that's the best, that's the optimal solution, and so it recommends that 16% change. It's a very simple concept, but it allows us to do that all along the corridor, and then hopefully come up with better progression for that corridor. So this is an example just to show you